In the next part of this section, we're going to be looking at a generalization of the linear mass density that we just talked about. With linear mass density, we were looking at the mass of a one-dimensional object, essentially the mass of something that could be represented by a straight line. Here we want to think about the mass of a two-dimensional object, something that for all intents and purposes can be represented by a thin disk that we could put in the plane, for instance. So it's a little bit difficult to do this in general with one variable calculus. When you get up to multivariable calculus and you start working with more general coordinate systems, you'll have much better tools for analyzing this type of problem. But with one variable calculus, we can at least analyze some of the more elementary varieties of this problem. For instance, looking at this question here, what about the mass of a very thin disk where the density at a point depends only on the point's distance from the center of the disk? This last kind of qualification here, density only depends on the point's distance from the center of the disk, is the kind of restriction that we need to add in order to do this problem with one variable calculus. So what's the idea here? Well, the idea is that in the plane you can have some kind of disk, so some kind of circle. Certainly we could center this at the origin. And the idea is that at each point we can talk about density still. This time what we want to do is, rather than talk about density as mass per length, we want to talk about density as mass per area here. So in other words, if we, so constant, a constant radial density here, let's call that radial density rho again, is going to tell us that mass is equal to rho times area. Now that we're working with a two-dimensional object, we have this notion of area to talk about that we didn't have before. And so this is going to tell me basically that I want to think about the density here as being mass per area. But again, we don't really know what, or we maybe want to generalize this to talk about shapes that don't have constant radial density. Maybe they have varying radial density. In other words, what that means is that maybe you are very dense towards the center of this disk, and maybe you're not very dense out towards the middle. Or maybe you're not dense at the middle, but or not dense at the center of the disk, but sort of somewhere in between, you're like very dense, and then way out at the edges, you're not dense again. We want to be able to analyze the mass of something like this if we only know the this radial mass density function. What exactly does it mean for the density to depend only on a point's distance from the center? Well, it means that all of the points on a given circle have the same density. So in other words, points here, we might have, that's supposed to be a circle, might have density 5, and points, let's say here, might have density 1. But the important thing is, if you take 2 points which lie on the same circle, in other words, 2 points which have the same distance from the origin, then they're going to have the same density. So that's sort of how we want to interpret this. 2 points of the same distance from the center have the same density. Note that this still allows us to have varying density. Certainly we can talk about, this green circle satisfies this property that 2 points of the same distance have the same density, and this purple circle does as well, but the green circle and the purple circle have different densities there. So again, what we can do here is we can now think about rho here, so this radial mass density function, we can think about it as a function of x. because each x value here determines exactly what the determines a circle centered at the origin. Namely, if I pick the x value here, I can draw the circle centered at the origin with radius x. And once I know how far away I am from the origin, that tells me exactly what my radial density is. So given an x value, I can always find a radial density for every point with the same distance from the origin as that x value. So here we have rho being a function of x, because 2 points of the same distance have the same density. Great, so now that we can think about rho as a function of x, what we want to do is we want to, again, split up the interval from the origin out to the radius of this thing. So if our disk, for instance, has radius r, actually let's make this a capital R. If our disk has radius capital R, then what we can do is we can split up the interval from 0 to r into a bunch of small little subintervals. So maybe here I'll pick the point x, and I'll draw a little circle, or a circle that is a little bit larger. Maybe the width here is dx. And in order to compute the mass of this little disk here, I want to compute the mass of this little disk in order to add up all of the masses of each of these individual disks. So the mass of the blue disk here is approximately equal to, well, if I chose this width to be small enough, the mass density is going to be roughly constant on this disk, because the mass density is certainly constant on the inner circle by how the radial mass density function works, and the outer circle is not very far away. We're going to be certainly assuming that the radial density function is continuous here. So since the points in the outer circle are close to the points in the inner circle, their densities are going to be roughly the same. So we can assume that the density is roughly constant, so the mass is then going to be roughly equal to the density at point x times the area of this disk. Well, the surface area of this disk is again going to be roughly the width, dx, times the circumference of this disk. And the circumference of this disk is roughly 2 pi x, because this is a disk of radius x. So in order to compute the total mass of the circle here, this circle that I've drawn in black, this is going to be equal to what we would get if we added up the masses of all of these tiny little disks here. So the total mass is going to be equal to the integral from the smallest x value. Well, x here we're thinking about as the radius of one of these circles, so the smallest possible radius that we could have would be 0. The largest possible radius that we can have is big R, and we want to integrate this, the masses, or we want to add up the masses of all of these little disks. And so what that looks like is 2 pi x times rho of x dx. So given this rho of x function, or this rho function which gives you the radial mass density, meaning that the density is constant on any circle centered at the origin, then we can integrate rho of x times 2 pi x, and we can get the total mass of the object itself. So let's take a look at an example. We have a black hole of radius 12 gigameters, and it has radial mass density function rho of x equals 10 to the 30th e to the minus x squared kilograms per square gigameter. I made a typo here. It should be correct in your version of the notes, but it is not correct in mine. And we want to know what is the mass of this black hole. So I'm not really sure if this is actually how computing masses of black holes works. I kind of just made up this problem to fit the flavor of the radial mass density sort of function, it seems plausible that a black hole might have a radial mass density function, and it's certainly the case that we're not about to get the mass of a black hole by putting it on a scale. So this seems like maybe a plausible approach to looking at how to compute the mass of a black hole. However, it might also be completely implausible because maybe a black hole isn't actually well approximated by a thin disk. Maybe black holes have some kind of thickness. Not being an expert on black holes, I guess I am not one to judge there. But if you know, tell me, and then I can maybe fix this problem or scrap it or know that it actually worked. So in any case, we're going to assume that this is how black holes work for the purpose of the problem, but don't go walking around and telling people that you can compute the mass of a black hole by integrating a radial mass density function. Anyways, so let's see. So we're assuming that this is how it works, and so we know what we need to do is take an integral from 0 up to the radius of the thing. Well, great. We know that that is 12 gigameters. We have this radial mass density function, rho of x equals 10 to the 30, e to the minus x squared kilograms per square gigameter. So what we want to do here is we want to integrate 2 pi x times rho of x. Well, rho of x is 10 to the 30 e to the minus x squared. And we want to integrate with respect to x here. Great, so factoring out our constants, and I'm going to leave the 2 in there for the moment because it's going to actually make it a little simpler. 10 to the 30 times pi, integrate from 0 to 12, 2x e to the minus x squared dx. So this integral requires us to do a u substitution. I'm going to notice here that I've got this minus x squared in the exponent, and I've got its derivative, or close to its derivative, sitting handily outside of the exponential there. So I'm going to let u equal minus x squared here, so that d minus du is equal to 2x dx. And in order to compute this integral, then, we have 10 to the 30 times pi still sitting around out front. We have the integral from, let's see, 0. We'll leave these as x values for the moment. X equals 0 to x equals 12 of, let's see, so we have e to the u times minus du. Great. Oh, we should maybe make that clearer. All right, so now we know how to integrate e to the u. It's just e to the u. So this is 10 to the 30 times pi times minus e to the u, evaluated from x equals 0 to x equals 12, which is minus 10 to the 30 pi. Let's see, e to the minus x squared, evaluated from 0 to 12. So we're going to, let's see, evaluate this thing at 12. So we'll get e to the minus 144. E to the 0 is 1. Great. All right, so we have this number here. I promise it does turn out to be positive. This quantity here, e to the minus 144 minus 1 is negative, times this negative sign gives you a positive number. So we get some kind of positive mass here. And the last thing that we want to do is we want to check out the units on this thing. So I guess we aren't told what the units on x are. I suppose I should have done that too. X here is measured in gigameters. So let's see. So now that we have units on x, we know that the units on the integral are the units of the integrand times the units of the variable. We just learned that the variable gives us units gigameters. This 10 to the 30 e to the minus x squared component gives us units kilograms per gigameter squared. And this 2 pi x here, well, 2 pi doesn't have any units associated with it, but x does. X has units gigameters. So if I multiply all of these units together, I notice that I have 2 units gigameters in my numerator, canceling out the 2 in the denominator. And in fact, so I get that the units here are in kilograms. Cool. So we have some number of kilograms here. This is quite a large number. All right, I think that's where we're going to leave off with this video. We've finished more or less our mass computations. We'll look at some more physical applications in the future.